Simulation and Analysis of Machinery Fault Signals by White, the Ship Research Institute of Norway, revised 7th of June 1982, and today is, and it was revised 5th of May 1983. Today is June 9th, 2015. Machinery condition monitoring is rapidly finding applications in all branches of industry. In particular, vibration monitoring is playing an increasingly important role as a tool for assisting with predictive and preventive maintenance and for improving operation efficiency of plant. Condition monitoring systems are used for the detection of incipient failure and the diagnosis of the nature of faults in operating machinery. However, for these systems to be reliable, an improved understanding is required of the vibration signatures produced by machinery failure mechanisms and of methods for the interpretation of these signals. Many types of fault produce vibration signals which are impulsive in nature and which may be buried in background noise. That's right, buried in background noise. A method is described for simulating the type of signal and modeling the various stages of incipient failure. Statistical and spectral analysis are used to describe the fault development. The influence of machinery frequency response characteristics on signal transmission from the damaged area to the measurement point are also considered. So a typical fault signal is assumed to be impulsive in nature because of the way in which it is generated. In the case of journal bearings or gears, for example, surface defects will produce pressure fluctuations in the lubricant and the oil film between sliding surfaces may also momentarily break down, causing impulsive contact to occur. With rolling element bearings, the interaction of defects will produce a pulse whenever the defect strikes or is struck due to the rotational motion of the system. The variations in contact load caused by damaged areas in the above situations will therefore be periodic in form, with the repetition rate of the pulses being governed by the rotational speed of the machine. Consecutive cycles, however, may not necessarily be exactly repetitive because of factors such as slip and rolling elements bearing or the hunting tooth design of gear trains. So read about that. Yeah, this goes on and on. Read about practical signals and the effect of pulse shape on spectra, a random pulse train, generation of pseudoperiodicity, generation of random pulse width, analysis methods. Vibration analysis falls broadly into two main regimes, the time domain and the frequency domain, and both are used in condition monitoring. Statistical analysis, experimental results, half-sine wave pulse trains, system response to pulse train excitation, pseudo-periodic pulse trains with randomly varying pulse width, system response to randomly varying pulse width, kurtosis measurements, comparison of model test results with rolling element bearing life test results. So conclusions. Pulse trains used to model machinery fault signals produce characteristic line spectra where the line spacing is controlled by the pulse period and the peak envelope is governed by the pulse width. The introduction of random variations of pulse width into the signals produces sidebands on the discrete spectral line at spacings governed by the percentage variation in pulse width, with both random pulse width and random periodicity introduced in the pulse train. The higher frequency content of the spectra increase. Very large random variations in pulse width and periodicity produce spectra approximating in nature. Kurtosis level to 3. With a small additional noise component, only the high frequency ranges are affected at low pulse repetition rate. And since the low frequency values of kurtosis do not change, the peak is effectively translated to a lower frequency. For increased pulse repetition rates, however, the peak kurtosis value is translated to the mid-frequency ranges, but peak levels are little more than 3. These results suggest that kurtosis will be a very useful monitoring parameter in situations where pulses contribute significantly to the signal level. Acknowledgements. The author gratefully acknowledges support by the Science Research Council of this program of research carried out at the Institute of Sound and Vibration Research in Southampton, England. References include Dyer and Stewart, 1978, American Society of Mechanical Engineers, Journal of Mechanical Design. Detection of rolling element bearing damage by statistical vibration analysis. Elmore and Held, 1969, Physics of Waves. Morse, 1948, Vibration and Sound. Harris, 1961, Shock and Vibration Handbook. Robson, 1963, Random Vibration, Edinburgh University Press. Olson, 1969, Frequency Analysis of Single Pulses. White, 1977, Institute of Sound and Vibration Research, University of Southampton Technical Report, number 97, The Modeling of Structural Systems and Signals for Machinery Condition Monitoring Studies. So read about the simulation and analysis of machinery fault signals. Simulation and analysis of machinery fault signals. Simulation and analysis of machinery fault signals.